Hi everyone, so in the previous video we talked about charging circuit, so now let's move on to talk about discharging circuit. Okay, so it's a continuation of the previous video, and this is on section 3 on charging and discharging circuit. But right now I'm going to talk about discharging circuit. Okay, so for discharging circuit, I believe you can notice a difference from just now. It's that there's no longer a battery in the circuit. So if there's no battery in the circuit, what happens is there will be no power supply pumping charges from the lower potential plate to the higher potential plate. You don't have such a pump anymore. So right now what you are left with is a charged capacitor. Okay, it's initially charged when to discharge the capacitor. So the capacitor here will have a high potential plate and a low potential plate. So what happens is, because there's no longer a pump over here, what happens is the charge will naturally want to go from the high potential region back down to the low potential region. So you have charges being coming out from this plate over here, coming back down to this plate over here. Okay, so this process over here, it's the process in which the capacitor is losing charge. So if it's losing charge, that means by the capacitor is losing energy. So if it's losing energy, what does it mean? It means that right now the capacitor has played another role. Instead of taking out the energy from the battery to be stored, right now it's using the stored energy to release it to the circuit. It's releasing the initially stored energy to the circuit. So if it's releasing the energy, how is it released? By releasing the charge from the upper plate for the higher potential plate to the lower potential plate. So when the energy is being released to the circuit, who will be accepting the energy released from the capacitor? It will be the resistor that accepts the energy. So who is the provider of the energy? The capacitor. Who is the receiver of the energy? The resistor. Okay, so this is just a discharging situation. Okay, so if you think about it, we can make a statement by saying that the energy right now is supplied by the capacitor. That's why you can say that energy supplied by capacitor. So who will be accepting the energy that is supplied by the capacitor? It will be the resistor that is accepting. So it's energy received by the resistor. Okay, so if you want to put it into a form of equation, previously I would say that the energy can be directly correlated to the voltage or the potential difference. So energy supplied by the capacitor will be represented by the voltage across the capacitor, whereas the energy received by the resistor can be correlated to the voltage across the resistor. So you can come to a statement that VC is equals to VR over here. There is no power supply involved, so there's no VS in this case. VC, we know that it's just Q over C. Okay, this is what we know based on the definition of capacitance. And then we also know that the definition of resistance is the ratio of V over I, so that's why V here is equals to IR. This is Ohm's law. Okay, so based on this, what we can say is, we know from our discussion earlier, capacitance and resistance, they are fixed. Okay, if you're using a certain value of capacitance, as long as you're not doing anything inside the capacitor, your capacitance will not change. So you should expect that the capacitance is constant together with the resistance. The resistance should also be constant, because you remember resistance has color bands, right? It's impossible that when you're discharging a capacitor, slowly the color bands has changed color. It just doesn't work that way. As long as you don't do anything inside the resistor, let's say you change the resistor size, you change the material of the resistance, resistor, if you are not changing anything inside the resistor, you are not able to change the resistance at all. So the R and the C should technically be the same. So what happened during the discharge process is you're losing charge, right? So if you're losing charge, you expect that the Q should be decreasing. So the decrease of Q will result in our voltage across the capacitor to be decreasing, okay? Because you have C which is constant and Q which is decreasing, so overall Q over C here will be decreasing. So you know that it's equal, that means VR over here should be decreasing as well. So if VR is decreasing, and we know that R is constant, then what must be decreasing is the current. So that the current over here should be decreasing. Okay, so it's sort of a set situation. Everything is decreasing, nothing is increasing over here. So let's write down our conclusion on this side. We know that the decrease of Q causes a decrease of VC, whereas a decrease of I causes a decrease in VR. Okay, let me label first. This is a fully charged capacitor initially. And it has been discharged until it becomes uncharged. Okay, so this is a discharging process. Okay, let me review what happened previously. How do I label it? Yes, okay. So it's a similar idea over here. Oops. You know that fully charged capacitor, the moment you close the switch to connect this circuit, discharging will start to happen. So when discharging starts to happen, you have charges moving from the high potential plate to the low potential plate. But let's draw a fully charged capacitor first. A fully charged capacitor will probably look something like this. Okay, so there's plenty of positive charge on one plate. The other plate will be negatively charged. Okay, so right now it's fully charged, right? So you can say positive Q naught over here. Then you can say this point over here is negative Q naught. It's maximally charged, maximally charged. So we can say that the charge stored is at its maximum. So Q is equals to Q naught. Okay, so because the charge store is maximum, you should expect that the uniform electric field is the strongest at this moment. So you know that E is equals to V over D. So you have strong electric field, you have strong potential difference. So you should expect a great potential difference across the two capacitor plates right now. So VC over here is at its maximum, so you call it as V naught C. It's at its maximum voltage across the capacitor. So this is what we have right now. So right now we are also going to study the voltage across the resistance, and we're also going to study what happens when the current or when the charge flow back out from the high potential plate to the low potential plate. What happens to the current? Okay, so this is the same as what we discussed just now. We know that VC is equals to VR, so VC is equals to VR. Again, we expand. This is just Q over C. This is just equals to IR. Okay, so what happened? We know that Q initially is fully charged, right? So because initially is fully charged, we should expect that this charge is maximum right now. Okay, so we can say what happened right now is Q is maximum. So Q is maximum tells you that your VC over here should be a maximum. And because VC is maximum, you know that VR is the same as VC. So you can know that VR should also be maximum. So VR is maximum is due to what being maximum? Well, it's not due to R. R doesn't change anything. So the only thing that can change is I. So if VR is maximum, I will be at its maximum. So you have maximum current right now. So you can say current is maximum. Okay, so this is what we have initially when we just close the circuit to allow for the charge to start flow back to its low potential plate. It just started, so initially at time is equal to 0, you are fully charged, your Q is max, your VC is max, therefore your VR is max, that's why your I is max. But as you discharge capacitor along the way, you see a decrease in Q, you see a decrease in I, decrease in VC, decrease in VR. So at the end of the journey, you should expect that the capacitor become uncharged totally. So uncharged means that there's no charge being stored at all, so you should expect it to be neutral right now. Okay, so this is the capacitor plates being neutral right now. So I'll write this as 0. I'll write this as 0. So right now the charge stored, there's no longer any charge stored, so we can say the Q is now equals to 0. And because there's no charge stored, you should expect there's no potential difference anymore over here. Should say Vc is equal to 0. Okay, so analyzing using the same equation, which is Vc is equals to Vr. What happened right now is everything dropped to its minimum, which is 0, right? So you should expect that if you open it up into Q over C and IR, you should expect that the Q has already become 0 and I has already become 0 as well. Okay, so what happened is your charge has went to a minimum. Okay, then your Vc will be a minimum. When you say minimum, it's 0 lah. Okay, it's equals to 0. Okay, so your Vr will also be a minimum. So that means by your current should also drop to a minimum. Okay, so I think it's really straightforward compared to charging where there's something increase, something decrease. In discharging, everything just decrease. Okay, so you know that everything just decrease, you can proceed to talk about the graph actually. You should know that the graph should all trace out a decreasing pattern. So we have charge stored, we have voltage across the capacitor, we have current, and we have voltage across the resistor. We have 4 things which we need to investigate. And based on our understanding, all of them will drop, all of them will decrease based on our explanation over here. But what kind of pattern does it trace out? I believe all of you actually sort of know that it will trace out an exponentially decreased pattern. But let me just bring you a bit to animation to sort of explain the exponential kind of relationship, how it comes into place. Then only I come back here for the graph. Okay. Okay, so this was the explanation just in the previous video when I talk about charging. So at the end of the charging process, you see that the force exerted by the battery to pump the charges in this direction will be balanced by the repulsion force between the positive charges to push the charges out from the plate. So there's force trying to push charges in, there's force trying to push charges out. So when the force in and the force out, they are equal to each other, then the charge can no longer be going in or can no longer be going out. So you can say that the charge stored in the capacitor has come to its maximum. You can no longer put in any more charges anymore. Okay, so you reach Q0 at the end of the charging process, which will happen at infinity. Okay, so right now what we're going to do is we are going to remove the battery. Okay, and we are going to close this circuit over here. So try to notice, if I remove this battery over here, that means by the component that is playing the role of pumping charges up into the high potential plate is no longer existing anymore. This force over here will no longer be existing because the battery is already absent in our circuit over here. So there's no longer this force acting by the battery to pump charges to the high potential region anymore. So this is what we have right now. If you connect this circuit over here, we are only left with this repulsion force between the positive charges. There's only forces that try to push the charges out from the high potential plate. There's no longer any forces to force charges into the high potential plate. So what happened right now is, if we start with this particular situation where we connect the circuit as time is equal to 0, at time is equal to 0, you can see that the amount of charge we have is maximum, and the electric field that we have in between the capacitor plate is also maximum. So you should expect the voltage across the capacitor to be also at its maximum. So Q is at its maximum, that's the maximum amount of charge stored. The electric field is the strongest, so you should expect that the potential difference across the two plates will be the maximum as well. Okay, but right now when we start the process of charging, what happens is there's only this positive kind of repulsion that try to push charges out from the plate. And initially there's a lot of positive charges in this positive plate over here, so you should expect a very strong repulsive force to push the charges out from the positive plate. So you should expect that charges are gushing out from the plate into the connecting wires at the start of the discharging. There's too many charges, there's a strong repulsion, charges will try to gush out from this positive plate because of the repulsion force. So you should expect that the amount of positive charges in the high potential plate will decrease very fast initially. It decrease very fast because they are all gushing out due to the strong repulsion. Okay, so this strong repulsion will cause a lot of charges to gush out. So they will gush out, then they'll go from high potential going down to low potential, then they'll be deposited on this lower plate or this low potential plate over here. So because it gush out very fast, then you can see that there's less positive charges left in the positive plate. That's why the repulsion force also decreases. Just now there's a lot of positive charge, there's a strong repulsion. Now the positive charge not so many as before, so the repulsion force already decreased. So if the repulsion is not so strong anymore, then the charges are not so desperate to move out. Okay, initially there's a strong repulsion, you are desperate to move out. Right now there's not so strong kind of repulsion force, so you're not really desperate to go out. So if you're not really desperate to go out, you should expect that the charges that go out will be less. Okay, so right now we have our charge store is not the maximum anymore. There's some already returned back to its lower plate already. The charge store is not maximum anymore. But at this stage here, okay, the voltage across the capacitor also decreased already due to the decrease of charge. So this one also decreased as well. But due to the reduce in the repulsion force, the next step over here will have less positive charges moving. Just now it was 3, right? So it dropped very fast. It all gushes out from the capacitor. So the voltage also dropped very fast initially. But due to the reduced repulsion force, the positive charge that went out become less already because they're not so desperate, because that is not a strong repulsion force anymore. So less charge are flowing out from the positive plate to the negative plate. So you can see the reduction of the repulsion force once again, and the charge becomes even smaller right now. But the rate of it decreasing is not as severe as just now. Just now it's gushing out, but right now it's not so desperate, it's just coming out. Okay, coming out due to the reduced repulsion force, not so desperate anymore. So you should also expect that the electric field between the plates to be even weaker right now. So you should expect the potential difference to grow weaker as well. But again, you can see that the severity of the drop is not so severe anymore because the charge gushing out now is less than before. It's still decreasing, but it's decreasing at a slower rate. Just now it decreased very fast, now it's decreasing slower. So the voltage also decreased very fast initially, now it's decreasing slower. Okay, so again, if you are able to observe what's happening in this inside the connecting wires, you see that initially there's a lot of charges gushing, going back to the low potential plate. But as time goes on, you see that there's less charges moving in the connecting wires back to the lower plate. So you should expect that the current to actually be decreasing as well. Initially gushing out a lot of charges, now not so gushing out, just coming out, so not many positive charges. So you should expect that the current to be dropping. So if you continue this journey until time is equal to infinity, what happens is all the positive charges that should already move back to its lower plate. Then by that time, the positive and the negative charges in one plate has already balanced out. So this plate become neutral, this plate also become neutral. So when you become neutral, there's no longer positive repulsion anymore because it's net neutral. So there's no longer positive repulsion, so charges will not come out anymore. So that it has already reached its minimum amount of charge stored, which is 0. Okay, but this thing happened at time is equals infinity. Means right, it takes forever for the last charge to come out back to the lower plate. Okay, so the discharging process technically effectively takes forever to happen. Okay, but when you reach this stage already, you should expect that the amount of charge stored to reach 0, and because the amount of charge stored has reached 0, you should expect that it to touch 0. But again, it happens at infinity, so what we're going to do is we're going to approach 0 but never really touch 0. It's going to touch the line 0, q is equal to 0 at infinity, which cannot be fitted into this line. So that's why we are saying that we are approaching 0 but never really touch 0. Okay, so observing the uniform electric field, you should expect that there's no longer electric field in between the two plates, because right now both plates are neutrally are neutral right now, electrically neutral right now. So there will be no electric field inside here. So you should expect that the voltage across the capacitor to drop to 0 as well. But again, it drops to 0 at infinity. So right now it will just approach 0. Okay, going down to the current, again, you can see that it's getting weaker and weaker current because initially strong repulsion force, a lot coming out. Now less repulsion force is not coming out so desperately. So again, you expect that the current to be falling until it reach near 0. So because I mentioned just now, the last bit of charge here takes forever for it to come out. So you cannot say the current reach 0. The current can only reach 0 when it is at infinity. As long as it's not at infinity, you will still be having current, but very minimal because it is very near to 0 right now. Okay, so you can see that all the Q, V, and I over here should be dropping, and this explanation here hopes it can help you to understand why is it dropping in an exponentially decreased kind of fashion. Okay, so this also reaffirms our idea that every graph should look like an exponentially decreased graph. Okay, so moving on from here, let's fill in this this graph that we have over here. All of this graph here should be decreasing, so you draw a decreasing graph for everyone. So it decreased from its maximum Q naught, it decreased from its maximum V naught C, it decreased from its maximum I naught, it decreased from its maximum V naught R. Okay, so all of these graphs should be decreasing until you approach 0, decreasing until you approach 0 as an asymptote. This is an asymptote over here. Okay. Yes, it's all decreasing. So I believe we have discussed from a previous video, if it's an exponentially decreased equation, the equation don't have 1 minus, right? Okay, so the equation will be the standard exponentially decreased equation. Q is equal to Q naught E negative T over tau. Whereas this one is VC is equals to V naught C E to the negative T over tau. This one is I is equals to I naught E to the negative T over tau. Whereas this one is VR is equals to V naught R E to the negative T over tau. So all of these equations should share the same structure. There's no 1 minus because you are not in an increasing trend anymore. Okay, so these are the equations that we can use to describe how the charge stored, the voltage across capacitor, the current, and the voltage across resistor change according to time. Okay, and again from this graph, we can extract something important, which is called the time constant. Okay, so time constant is the symbol of tau. And once again, symbol of tau, the unit of it should be in second. Okay, or any time unit. Mostly we use second. Okay, so again, what is time constant? Is the time taken for something to increase or decrease to what level of its maximum value. Okay, we know that all the graphs are decreasing, so we don't need two kind of definition, just one will do. It's the time taken for Q, it's the time taken for VC, it's the time taken for I, it's the time taken for VR. All four of these things will be decreasing, so it's the time taken for all four of these to decrease. Decrease to what level? Decrease to 37%. Okay, 37 comes from where? Comes from this kind of derivation, saying that this is the equation at time is equal to tau. You can put it in, E is equal to it becomes e to the power negative 1, which is 0.37. Okay, so it decreased to 37 of its max value. Okay, so 37, please make sure you know that this is e to the power negative 1. Okay, so from our understanding, what can we say? We can say that if we look at the time tau over here, if we trace back what is the value of charge right now at tau, you see that it's 0.37 of Q naught. Same idea, if you take the amount of time tau and you observe the voltage across capacitor, you also observe that it's 0.37 V naught C. Continuing from there, you can also find current. So this is 0.37 I naught. Then lastly, you have another tau over here, which if you find the value, it should be equal to 0.37 V naught R. Okay, so this is how all the graphs should be decreasing, and when you reach the amount of time duration, which is tau, you see that all of this value here has really dropped to 37% of its initial value, or the maximum value. Okay, this tau value over here is it can be theoretically found using a very simple equation. You can determine the how much time it takes tau by using this equation. Tau is equals to RC. If you take the resistance multiplied by the capacitance, the value over there will let you know how much time does it take to drop to 37% of its maximum value. Okay, so I believe this is very similar to the charging circuit video. It's just you just need to understand this part, and I think the rest is just similar kind of explanation. Okay, so that wraps up my explanation for chapter 2 section 3, and actually chapter 2 I've already wrapped up my discussion. So that's it for now. Thank you very much.